Welcome to my little session here. My name is Richard Elling. I work at Viking Enterprise Solutions. Viking Enterprise Solutions is a division of Sanmina Corporation. And if you've been in around memory and so forth for some time, you might recognize our sister company or sister division, which is Viking Technologies. Viking Technologies does DIMMs and non-volatile DIMMs and SSDs and so forth. Viking Enterprise Solutions is the compute and storage group. So we make boxes, big, deep JBODs, NVMe devices that are sold primarily through OEM and ODM channels. So it's not that uncommon to find our products out in the field, but it's less common to see our logo on our products because usually there's someone else's logo on it. But that's fine. We're here to help everybody. And so I wanted to then talk today about work we do in building out very large storage systems and very fast storage systems. And sometimes they're both the same thing. But usually we end up doing one or two ends of the barbell. One end of the barbell being the latest NVMe stuff, very fast, very low latency. The other end being very deep archive storage. We use things like ZFS. We use, that's highly reliable kind of storage. But from a systems perspective, we always hear people talk about, and they come to us with graph data from VMware, ESXi, and whatnot, and they show us this average latency metric. And it's really pretty meaningless. And so I actually named this talk, Average Storage Latency Sucks. Let's fix it. But in the best interest of being more politically correct, average storage latency is lacking. But in any case, it does suck. So let's fix it. The first important thing is, when we start talking about averages and means and medians and that kind of thing, if you're dealing with a normal distribution, that's a pretty good way to do it. There's almost nothing normal about the distribution of latency in our systems. So some of that math starts to become more difficult, and often we don't measure it that way. We just roll things up as an average because that's actually really easy to do from a computation perspective. I'll pick on hard drives because they're easy to pick on. It's really obvious when you have a seek, rotate, how those things work. And you know that if I have to do a long seek, then of course that's going to take longer. Rotation is going to be fixed usually at some sort of multi-millisecond number. And you can actually see that, you can study it. It's really easy to make benchmarks that expose these things. Flash SSDs are a little bit different, actually quite a lot different. And yet we still talk both of those things thinking about what our average latency is. When we start adding in fabrics, it starts getting really, really complicated. And if you're into things like over TCP, so NVMe over TCP or iSCSI, for example, then there could be a really long tail latency due to networking effects, which also blows away our nice view of the average. Also talk a little bit about ordering, reordering, multiple queues, and of course, as we know, all of these things are like light bulbs. They burn out, or at least incandescent light bulbs, they burn out. And there's error recovery and retry that also messes with us as well. So one of the observations we have from a systems level perspective is, if you can get rid of all the really slow I/O components in your system, then the average goes up. The average becomes better and everybody's life is better. And so this is the problem, in that all of our tools that we use to deal with this are centered around average latency. And I can assure you that VMware ESXi administrator will come to you as a storage vendor and complain about the latency. And they're looking at average latency. So it's easy to pick on hard drives. I've done that already a little bit. But let's pick on SSDs as well. We were off in the lab trying to get the maximum performance out of a system one day, and I took a trace sample of all the IOs that were going on. I'll explain a little bit more in detail how to do that later. But I traced all the examples and I plotted out the latency. And we had a nice average latency. Let's see, the mean median's 374, the mean is 303 microseconds. And so if I came to you and said, hey, I've got this SSD, it's getting 300 microsecond latency, that's pretty good, isn't it? Well, maybe. And you might say, oh, I'm happy with this number, 300, okay, I can deal with it. But we knew that it was better than that. And we knew that if we could understand better what was going on, we might have a better idea how to improve it. And so when we actually plotted out the distribution of latency, you can see it's not a normal distribution at all. It looks more like, Golden Gate Bridge. Things that look like Golden Gate Bridge, when I plot them out, make me unhappy, because that means that, a significant part of the time I'll be on the wrong span, right? I want to be on the right place and get it going right. And of course, the low latency here, let's see, the minimum latency is 69 microseconds. So of course, everybody wants 69 microseconds. Maybe that's what you see in the data sheet, right? But the reality is somewhere here between 69 microseconds and 931 microseconds is my samples. But most of them seem to be falling into one of these two buckets. So we dug in deeper and said, why is this? I would expect this bimodal behavior from a hard drive, right? Seek, rotate, am I near, am I far? Not from an SSD. And so we then plotted out the density. This is a density plot of the latency as opposed to the logical block address. So the LBA across the bottom, latency on the top, and you can see the effects of my latency, this 100 cluster here versus this 450 cluster there, is some function of the LBA address, which is exactly not what we expect from an SSD, right? So we're system guys, what do? What's the first thing you do when this happens? Is you replace that SSD with a different one, right? So then, obviously, there's something going on. There's a lot of smarts in these SSDs nowadays, and caveat, part of the story is this is an SSD from several years ago. So whatever the firmware is now, it's obviously going to be very, very changed. But the real point here is that if someone came in and said, hey, I've got this SSD, I've been testing it all day, I'm getting an average of 300 microsecond latency, you might be happy with that, you might not be happy with that, but you don't know that we have this strange pathological behavior based on the LBA range. And in fact, we do want to solve that in the system level somehow. Oops. There's another thing that happens on occasion that you'll see. This is a nice SDC trace, and let me kind of explain how this works. I'm on a iSCSI initiator, and I'm sending IOs down to an iSCSI server, and I'm measuring the latency from the start, which is here, to the end of that IO. So basically, I can queue the IO, I record that timestamp, it finishes, I record when it's finished, and we plot that out. So then, the way I've done this is progression of time here, and I believe that's nanoseconds, whatever the unit of measure here for time, or it's microseconds. Yeah, okay, so it's microseconds. So I got microseconds along the bottom, and then I've got latency here. So I've ordered or reconciled post-processing for each IO. When was it started down here? When did it end up there? And I've put those two things together and scaled it by the latency for the entire thing. And this chart actually shows quite a bit of interesting information besides the fact that we got stuck on one IO and it took 500 microseconds for it, but it also compacted the reply for everybody else. So we were stuck in a queue, and for whatever reason that thing took 500 microseconds, and it backed up everything in the queue. And then what you see here is the queue draining here very quickly. So one of the things that tells us, of course, is that I'm not bandwidth bound. Because if I was perfectly bandwidth bound, then I would have the same slope here on the start as I have on the end, but I don't. I have a much shorter end time. So whatever IO is coming through on that back end is, in fact, quite a bit less. I have plenty of bandwidth in this system, right? And then the other thing is, once we get back to a happy steady state, now I'm into fast IOs again. So if you do this then on a whole bunch of concurrent iSCSI kind of workloads, then you'll start to see these kind of behaviors come in, just totally due to the completion queue. But from a statistical point of view, this is my distribution of latency. And you'll notice it also is not normal distribution. So I've got two cases then, if I look at the distributions of latency that tell me that something is maybe not behaving optimally for me. And so one, I have the bimodal or trimodal, you'll see those things as well. And then the other distribution is, this is not normal, this is something more uniform distribution. And the average here is somewhere in the, I didn't do the detailed things, but let's say it's 320 microseconds or so. So the point is, if the guy comes at me and just gives me an average, it really doesn't tell me really anything about what's going on and what pathologies I might want to look for in the system. So another popular tool we get feedback from is IOstat. If you're not familiar with IOstat, it's the canonical, how am I just doing in Unix IO statistics. And I did kind of a couple of examples of that. The outputs will vary across distributions in Solaris versus Ultrix versus IRIX, whatever. And but in general, they're kind of all collecting data in the same sort of way, and that is inside the driver, we have a start time. We know when the IO is issued, and then we know when it finishes, and we take that difference in time and we accumulate it. And then I can take that difference in time by the total operations done, which I also count, and then that gives me an average. And a couple of things are interesting here. One is in Linux, for example, this is milliseconds. So you're working on a really high-speed storage system, and you're seeing latencies that are let's say 15 microseconds, then it's kind of useless to look at this number because it's not high enough resolution. Even worse, on my Mac, right? 0 latency, hey, can't beat that. But we know, in fact, it's just the measurement's not, showing me that measurement is just not good. And other things are, sometimes you'll find things like in Linux, there's a service timeout here, which is actually broken. It's not measured properly to begin with in the kernel, and therefore it's in IOstat, it's pretty useless. So those are more indications of where that IOstat gets, or the average gets pretty useless. So then let's look at how Linux does this. So for every device in Linux, every block device, with the caveat that this format is not stable across all releases. They've added some new fields to this lately. But this is kind of a kernel 7 or kernel 4, early kind of mid kernel 4 kind of time frame. And this is the stats. So for every device you have, then in proc.dist-stats, you can read that, and it's going to give you a line. And then in the line, we have first item is the major number, minor number, some version of the device name, which will change when you reboot anyway. We have completed reads, number of reads that are merged by the block device layer drivers. Right, what else we got? Sectors in 512K. Then there's an accumulation of time, milliseconds spent doing IOs, milliseconds, weighted number of milliseconds doing IOs. And so what IOstat is actually doing is reading these numbers for you and doing some math. And then if it takes samples over time, like you tell IOstat, give me samples every 10 seconds, it just reads it again, does the math and comes up with a number. So that's pretty good. Or really, that's all you get. So then, how can we do this better? There's a popular tool out there really gaining steam in the cloud native world. It's Prometheus. And with Prometheus, it's a pool model statistics collector environment. So basically what I can do then is on my nodes out here is I can run agents that read the dist-stats file, for example, and then set those up as data formatted for a time series database. Prometheus provides a time series, collated time series view into the systems. And then I can graph data in Prometheus using Grafana. So all of this stuff here is open source. It runs on multiple platforms, multiple OSs as well. And I'm pretty high on it. But basically, we're going to run these agents in the OS. They're going to collect whatever stats the OS deliver. In Linux, it's proc.dist-stats, for example. And they're going to throw those up so we can collect them. So obviously, if I'm collecting proc.dist-stats, I'm getting the averages. So I haven't really gained anything. I can still do an average latency plot, yeah, but it's the same data if I use IOstat. So it doesn't buy me much. But Prometheus has a nice little feature in that it says, hey, I can collect data with multiple dimensions on the datum. And so we can use one of those dimensions as a latency bucket. And now I can start to produce those statistical graphs that I get from observing traces real time on a real system. And then I can plot that as what's misnomered as a heat map. So there's a couple of different variations of heat map, but when I speak about heat maps in the sense of performance analysis, what I'm really looking at is here's my time on the bottom, right? Time series, it's going to be my experiment as it runs over time. And here on the left-hand column, these are my latency buckets. It starts at 1 microsecond. Why 1 microsecond? Because that's the units that Linux uses for time. I can get down to microsecond, sub-microsecond, not so much. And so we start here, 1 microsecond, 16 microseconds, up in powers of 2, and I just capped it at looks like 1 second at the very, very top. And so then I have time, I have my buckets, and then to get the other dimension of this, we use color. So this is a density plot as well. And so for all the IOs that complete within this time bucket, the more I have, the more dense it becomes, and therefore the darker the color becomes. Okay, so basically now over time I can observe my system and I can look at the latency as it's coming through, and then I can look at all those buckets and I can start to see, especially depending on which colors I choose, I can start to see if there's an outlier in one sense or another. So let me talk then about this experiment. This is 3 different disk storage systems on the back end of a key value store, which was etcd. And etcd is running the first system here. What do we got here? This is the disk back end latency, and then this is the write-ahead log commit duration. Okay, and you can see there's going to be some relationship, but because the write-ahead commit goes to disk, and therefore I have two different latency measurements going on here, and they may or may not be aligned. In this case, they're actually fairly well aligned. But so my disk latency here is running in the 65 to 250 millisecond range. So I'm really kind of pounding it a bit. The middle one, this is a flash SSD, and obviously we have much better latency. You know, we're kind of averaging for log commits around 1 to 2 milliseconds, and then onto the disk, you know, we're in the 2 to 4 millisecond kind of range. Nicely bounded. You know, this kind of looks more normalish. This makes me happy. And then the one on the right is RAM. So if I eliminate basically all physical block I/O and I just go to a RAM, what does that same workload look like? So you can see basically same experiment, 3 different storage backends. All of them kind of give me a nice normal distribution or thereabouts. And then we can see that my latency goes down and life is better. Now then, when we come back in and want to analyze the system or look for extenuating circumstances, then I'm afraid it doesn't really show up too much here. But you know, there's a couple blocks up here that are a little bit lighter color. And I wouldn't be too worried about one that's kind of close to my distribution here, but if I had a block that was way up here on the top, then yeah, okay, I got a problem I need to go look at in more detail. So just looking at the shape of these curves allows us to very quickly get a view on how those work. So I have a way to display this stuff. I can do it in real time. And it's more interesting to me than average latency, right? So we're making progress. The next question is, how did I get this data? At which case I start a few shameless plugs. One of the ways we've done this for several years now is using DTrace. DTrace is available on your Mac. If you don't use it, you should. It's also available on FreeBSD, of course. Kim's out of the Solaris world. And I'll talk about BPF as well. So let's then look at, if I wanted to measure latency histograms, how do I do that in DTrace? And this is where you should say, oh, wow, that's simple. Well, I just do that more often. Yeah, exactly. So here's the latency thing, and basically here's how it works. When there's an I/O and it starts, so we're starting into the issue of an I/O, then we record in a variable called start. We record the arguments to the I/O, which includes information like the CDB in the case of SCSI. And we set that to the current timestamp. So basically, this is time now. So I'm building up an array. The array is called start. The arguments for the array is basically everything unique to that I/O. And then I set the value to the timestamp. And then when the I/O is done, right, we're exiting that function, or hitting the DTrace probe in this case, and the value of timestamp here is not 0, or actually exists, has some value in it. Then in that case, we want to record in a bucket what that value is. So I'm accumulating now into a new variable called time, which is, I didn't write this, but it's a terrible name to use, but okay. We accumulate into time, we're going to label it as disk I/O latency, and we're going to quantize the difference between the current time and the start time, which is our elapsed time or the latency, right? And then, just so we don't enter this again, we set the value to 0. So, very simple code, right? We do this very easily. I can run this on my MacBook. I can get data. Life is good. What does it look like? It looks like that. So this is just running the script. I let it run for a little bit. I hit Control-C, and it gives me this nice latency bucket. So again, you'll notice the values are some amount of time. In this case, it's nanoseconds. It's bucketed in powers of 2, and then I get a distribution out here, right? So again, now I have something I can work with. I can take samples. I can do this on my terminal. I can do this into Grafana. I can take a look at these things. And again, we see this sort of normal-ish. I mean, this thing has it's whatever was running on my MacBook at the time. But it has kind of a nice SSD-like response time, which I expect. I've got a couple IOs for some reason way down here that are very long. I'm not sure I'll do anything about it. I mean, what can you do on your laptop, right? But it does give me a nice way to collect that. So that's how we do things, sample collections in DTrace. For Linux, we kind of don't have DTrace available as a first-class citizen, but there is this thing called BPF. So BPF, you'll hear people rant and rave about it. It's has many of the same characteristics as DTrace. It allows us to build scripts that sample things, and basically it's pretty similar to things like SystemTap, where I can also build collectors for this sort of stuff. And also at various times you'll see it referred to as eBPF, extended BPF. But really the whole idea is not necessarily that I turn everybody into a BPF coder, because to be honest, that's not going to happen. What the reality is that there's already existing people like myself who write BPF scripts that look at some portion of the system and give me interesting results that we're interested in. Okay, so there are equivalents for doing things like basic I/O. I can break that out and get to it, and I can get the same kind of graphs that I did in the DTrace example. So I will put a plug in for Brendan Gregg, who's done a lot of work here. He has a book coming out soon on BPF performance tools, and that's going to be hitting here in a couple of months. I don't know the exact date, but it's coming on. And then there's some other good ones as well. Let's see. So how does Richard go from that sample trace to getting it in Grafana where I can see the pretty pictures? And there's a couple of good ideas. And one of those good ideas is what I got called eBPF exporter. So what this allows you to do is to create a YAML. And if any of you guys are Kubernetes people at all, YAML is your new way to speak to your wives and significant others and children. So we talk YAML, and basically it allows me to encode a BPF program, like one that collects latency for block devices, into YAML, and then it makes that program's results, which are all these latency buckets, available to me for a Prometheus scraper. Okay, so now I can take that YAML code and I can fire it at a system, have it run eBPF. It gives me all that code. I can have the Prometheus scraper come in and scrape it, and suddenly I have access to all this really cool data. So I can measure latency distributions, which is what I do a lot of, but you can really measure darn near anything. And if you have access to the source code, which we do, of course, then you can really set up some sophisticated data collection there. So we do that thing. But there's a problem with samplers like this. And the problem is, when the going gets tough, the sampler bail out. So this causes us a problem from a product development perspective in that, yes, I'd like to have this information. It makes my performance guy happy that they have access to this information, but I don't want it to impact my running performance of the production system, right? So, fortunately, this is a storage developers conference, and we're storage developers, right? So the people who need to fix this are storage developers, yeah? So we can fix that. So I can run a sampler, I can do a sample like I did on the DTrace with my laptop. I can run it, it's fine, it's great. Running those 24/7, especially on a system like we build with hundreds of disk drives, maybe not exactly what you want to do. If for no other reason than I know when the going gets tough, my sampler is gonna commit suicide, and therefore I'm gonna miss the important part of when everything's falling apart, right? There's of course also the security guys will stand up and say, wait, you can't run that as root, you know, but I'm looking at kernel stuff, and they're like, get off my machine. So that becomes a problem with security policies. And then of course, the other thing about writing codes like DTrace or BPF is I could actually write code that runs in kernel context that consumes a lot of resources. And maybe I don't want to do that. So it's pretty unusual for latency measurements that it's a problem, but it's very easy to do some pretty sophisticated scripts that really look at a full data pipeline, especially when we add networking into the mix, that can impact the overall performance. So we kind of want to be cognizant of that. Let's see. So the good idea next is I use samplers for debug. I use it for prototyping. I use it for lab work in my lab. I use it for emergency work in the field. I can copy and paste from an email and get sample data back from a customer without having necessarily to go through, download this binary and run it on your on your production system. No, that's probably not going to happen, right? And so we can kind of get into that. So the most useful piece is when we run that stuff in the code itself. And we have an excellent example of where this works really, really well. And that's Chrome. So those of you who use the Chrome browser, you'll be delighted to know that you have a URL at your disposal called chrome://histograms. And if you go there and look, you will see a very long page. And in that page, you're going to have all sorts of histograms related to events inside Chrome. So I just picked one for the heck of it. And it turns out there's a mouse wheel event collector, which is funny because I don't have a mouse wheel, but there's a mouse wheel collective in Chrome. And then I can see that, here it's giving me all my histograms up, and they go pretty fancy in that, hey, we've got the cumulative distribution here, right? Then I've got some buckets, which is great, and I get this little ASCII art kind of thing, so don't ask me why they do ASCII art in a web browser. Can't you guys draw pictures? But they're doing so well, I don't want to upset them. But anyway, basically, so for all the subsystems then in Chrome, they can collect this data. And there's a couple talks from the guys at Google where they actually pull this back and look at the performance of their systems globally and across various networks, because part of this data, there's a whole bunch of it, but part of it can be how long does it take to do DNS lookups, and how long does it take to transfer stuff over the network. And the whole thing is, once they had that information collected, then you can mine it, and then once you mine it, then you can look for areas of improvement, and I can start to whack out on these outliers, right? So they're one of my favorite examples of that. And I encourage you to take a look, it's kind of interesting. But we have realities when we start dealing with code in the kernel. And one of those realities is in JavaScript, if I'm collecting in Chrome, I'm collecting all this data. JavaScript doesn't have integers, it has numbers. And those numbers are floats. And I don't have necessarily floating point in my kernel, right? It's all integer. For all intents and purposes, for your life, think integer. And so some of these things have limitations. So one of the limitations is, okay, those guys are collecting things, they're putting them in floats, so they actually have a resolution problem that's not necessarily immediately obvious, but that's okay. For the most part, they get what they need. In a kernel, especially a long-running kernel, right? We run these things in production, they may run for a couple of years. Usually, back at Sun, we had machines that ran until you had to power it down to move it across the street to the new data center. And so, we do worry about integers and how they roll over. And of course, it's much safer and much faster to count integers than it is to do any kind of floating point stuff. And so, the kernel math is all, you just assume it's integer, and we work from there. So that's one of the limitations we deal with. Even if we're counting up IOs, we start counting up nanoseconds, right? Then we're going to run into, I'm counting a lot of nanoseconds because nanoseconds go fast. And now all these IOs, I'm doing millions of IOs per second, right? So even in the kernel level with 64-bit ints, I still have to start to think about when that thing's going to roll over. Fortunately, the post-processing things like Prometheus and InfluxDB and so forth have the ability to do that. So we're running in there. We do have limitations. So what I want to start showing you next is some things that we do in ZFS, and I'll show you, we'll get to some code in a minute, where we use integer math and we use this elapsed time sort of thing to give us information in detail about the system. And before I get there, I need to explain to you how the IO Scheduler works in OpenZFS. I apologize for the eye chart here. It is in a dashboard. So basically, an IO request comes in, and it's broken into 5, or more recently, 6 queues. And I have 6 queues that then I can schedule and wait and make priority decisions about, that then eventually get to the disk queue that then get into the disk. Okay, so this is in ZFS. We're writing above the block IO disk layer, and we have our own IO scheduler, so it says, hey, some of these IOs are more important than others, and some have higher priorities, and then there's things like, in particular, I'll be talking a little bit about the scrub queue. So when we do disk scrubs, which is important in a RAID system, we don't want those scrubs to impact production work, and so we want to deprioritize scrubs, which gets into a dueling requirement of I want scrubs to finish quickly versus I want scrubs not to impact my production workload. The good news is I can tune this, the parameters of this IO scheduler to give more or less preference for scrub IO, and that's how it's implemented. So that's pretty cool. And then on ZFS on Linux, I don't believe this exists yet in FreeBSD, guys. I can ask for the pool to tell me everything, show me my buckets for latency for all of these queues. Right, so this starts to get interesting. So let's take a look at it a little bit. So, I do have trim here. So there's a trim column. You can see I did 0 trims. Yay, life is good. So I've got all this going on. To be honest, this guy wasn't up very long. It doesn't have very many tick marks in the columns, but basically it shows me my all these rightmost columns are my ZIO scheduler queue columns. And so I've got trim, I've got some scrub work going on there, and then we have synchronous read, asynchronous read. In ZFS, I don't show any asynchronous reads here. Asynchronous reads are prefetch kind of workloads pretty much only prefetch. Most reads come into the synchronous read bucket, and then synchronous writes or writes that have to be immediately put to medium, and they come in, but most of the writes typically for common use are put into an async queue, and they get flushed, aggregated, flushed out to disk later. So now I can tell how much time am I spending waiting in these queues, which allows me to now go back in and tune the weights of those queues, right? So this is how I can now take a look at the system and say, well, maybe we'll trade off some performance here for some performance there, but I have the ability to tune that. Now then, if we go to the far left side, the total wait time. So this is what an application would see for disk I/O through ZFS, although it's not quite exactly there, but cache accepted. This is real physical disk I/Os, not cached I/Os in ZFS. But so I do have total read and write times, and you can see kind of the distribution of those. It without throwing Prometheus at this, it looks kind of normal. And you can see some things. Okay, I got some reads here that are 33 milliseconds in the 33 millisecond bucket, and then you were, oh my gosh, I got reads. They take 33 milliseconds. This is terrible. And then you go back here and you say, okay, well, they were stuck in the scrub queue for a long time, in which case I'm cool with it. I don't care about scrub. It can be really slow. I don't care. And so we can look at those that way. So basically, this gives me a lot of insight into how I'm going to tune the IO scheduler and what I can do there. And then I'll go further to say that we do this hierarchically in ZFS. So I can go all the way down to the very bottom disk drives themselves. And then as the disks get rolled up into a higher level, like a RAID VDEV, then I can look at its performance as well, and then all the way up to the very top of the pool. So basically, I can follow my organization of the RAID structure all the way down to the disk and all the way back up to the application side. Right? Of course, pictures are a lot better. So this is an example of an experiment where I do pictures here on the, this is mic work, but I make reads a different color than writes, because then it's really obvious. If I look at a graph, am I looking at read work versus write work? So here I've got scrub work coming in. If I hover over it, I see the distribution here, which is pretty cool. So I got a little bit of scrub work here that took a short period of time. And then I've got some what we call fill work, which is if there's no data to scrub, then scrubs go really fast. But if I actually have data to scrub, which I need to fill first, then I do fill work. So if you look at the time axis, you can see I filled it and I scrubbed it, and that's how that kind of works, right? And then if I dive down the next level deeper, now I've got my asynchronous queue, my read queue, write queue. I put writes on the bottom here, reads on the top, and now I've got all that data that was on that CLI display now showed off in real time, or showed off in time with my time access here. So now I can start to correlate events that occur with latencies that occur and where do they impact the system all the way up through all the various queues. So you can see I get an awful lot of information out of that. So one of the things we have to do when we put these things together is we have to decide how we're going to choose the buckets. And everything I've shown you so far, you'll see is log 2. Why is it log 2? And the answer is, computationally, it's very low cost. So here's some examples of what it looks like in code. It's half pseudocode. Basically, my elapsed time then is my now time minus my start time. I'm not going to get into the details of how you know what time it is. That's a whole nother hour presentation. But let's just say you know what time it is now and you know what time it started, so now I have an elapsed time. And now I can choose my bucket is going to be basically log 2, and that's how we calculate that. So it turns out that most of the compilers, Clang, GCC, have a built-in for count leading zeros. And this is a really lightweight way for me to get a logarithm, a base 2 log from with very few cycles. Now, this works for storage pretty good because we tend to have a couple orders of magnitude difference, but still sometimes it doesn't work all that great. And sometimes we'll break up certain portions of the system into give me a more linear kind of calculation. I don't do natural logarithms because that's floating point. I don't have floating point. But we can do a linear thing, and when you do a linear thing, I'm going to be doing some division. So those of you who maybe aren't instruction set architects or micro architects, just know that division is expensive in a CPU. And you'd like to avoid division at all costs. If you can do it some other way than division, your life is probably a lot better. We don't know how long division is going to go because it depends on the data being divided. So let's just say it's 10 to 40 times slower than an addition, subtraction, bitwise operator or something like that. And then the other problem that occurs when we take linear collections is you'll want to see if it's in your linear range. And so now I have an if statement, right? So now I've got branches to deal with. And branches also get computationally expensive. So I want to try to avoid that as best I can. There's a couple of things that occur, like you'll find some log linear work out there where we kind of try to reduce the cost overall, but still get some nice resolution, even when we're talking about orders of magnitude difference. They exist as well. What I would say is at least give us a binary, log2 collector. Those are pretty darn lightweight. And the next consideration is there's arrays of buckets. I'll show you some code in a moment, but the simplest thing to do is to make one global array, right? Each array entry responds to one bucket, and then I have that. The problem then is we're running on symmetric multiprocessors or NUMA machines, and that becomes now a cache line problem. So one way around that, one array per processor per bucket, right? So now I have a two-dimensional array. I've got that going on. We're doing some nice math. I can get that done. There's no atomics. Life is better. So the gotchas is getting time can be expensive. Some tools even like as much as I like Prometheus. Prometheus itself only does floating point values. So when we make a collector, before we send the data to Prometheus, we mask it. Because Prometheus can handle rollover to 0, but it can't handle, or you'll have all kinds of crazy experience after you get passed into the floating point side. And also, interestingly enough, requests that start but don't end don't have an end time. So kind of, I have to tell people, I can only tell you how fast it took when it's finished, right? When things break, that becomes important. So, here's my quick diversion into source code. Assuming I can do this. As it thinks. All right, someone measuring the latency here? Average. In the ZFS for Linux code, this is out there on GitHub. When we get done with an I/O, this is where we do the stats updates, and we do actually look at an awful lot of stats. But what I really wanted to come down here and show you is after we get through a couple of conditionals and stuff, the data I was collecting in those histograms is really just right here. Okay, so what I'm saying now is I get to this point here, and all I'm doing is here's an array. It's got my priority, which is my priority I/O column. Then I take the log2 of the difference between the time, and I increment it. Right. So This seems pretty simple. Now, a couple things about this. There's no atomics. If we're off by 1 or 2, who cares? But it still causes me cache line issues on a lot of processors. So it's pretty simple to add this in. It's much more complicated to make it really high speed, but we're clever programmers. We know how to do that, right? And so let's jump back into the slideshow here. So those are some of the gotchas. Oh, dang, I should have started a measurement here. So, since we're all programmers here, and I've hopefully sold you on the virtues of understanding our entire stacks and the latencies as we go along the way and how to collect the data. If you do nothing else in your coding, at least put in a counter for exceptional latency. Okay? Typically, when we go off to things like in a SAS fabric, I might put a threshold at 1 second, and you would be surprised how many IOs in a SAS fabric that's busy with hard drives take more than 1 second. It will shock most people, but it does happen. And so at least put a latency counter in there that says, hey, you know, I got these exceptional latencies. Maybe I should do something about it. And then, of course, make that thing accessible so that whether it's in ProcFS or even write your own code, somehow or another so that we can collect that data and throw it up into a time series database. We use Node Exporter or Telegraph as good examples of that. And then, in conclusion, hopefully I've convinced you to do some coding and we get this good information, and then system guys like I can use it. Average latencies are pretty darn useless for the most part. We really want to get the high latencies. We really want to know the thresholds. More importantly, I want to know those distributions to know if there's something else that's pathologically wrong in my system. And we can do that. I can sample it, yes, but it's much better if I build it into the drivers or build it into the applications. And again, good examples of that are Chrome. And then we've got some of it in ZFS. It's not as optimal as I'd like it to be at this moment, but that's a couple of examples you can learn from. And then please add this into your products when you get a chance, because it really, really helps the system, guys. And with that, I'm done. Any questions? I got one here.
You've got a lot of experience on Linux with the user space dynamic trace points in mid-4 version of kernels. But I can tie stuff like this together with application level intelligence that may or may not have been in the version I'm looking at from production cluster. Then I can really get to this. So I've had trouble with USDTs being working there.
I have trouble with USDTs on Linux as well. And yeah, and also there's ftrace in Linux, which I can set trace points there. In fact, a lot of the BPF scripts use the BPF facility to look at normal kprobes. What I started to do in userland was I started to trace libraries using BPF. So like libc. Well, I can trace any function boundary there as well. So with eBPF, I can trace it a function boundary, and then I can point it at a library like libzpool in the case of ZFS, or libc if you want to be very generic. And then basically I can start to see all the applications use of that in my space. I have had really good success with that in doing ZFS work, because we do a lot of ZFS debugging and development in userland. It's much more friendly when you blow it, really. So I have been able to have success in doing that, but I've not done a lot of like USDT probes. And I find most of the probes in ftrace to be pretty not where I want them to be, actually. So I've been doing a lot of that in BPF lately. So.
That's
Needs symbols. There is a, and if you're doing Java, okay, good. Anything that's just in time compiled, right? It changes. All the symbols are different and they're dynamic, and it's really difficult to track through. Yeah, yeah. So the Java guys, yeah, I wish them luck. I don't program in Java anymore. Brendan's done a bunch of that stuff because he has to. But yeah, it's he's got some interesting talks and explanation about how to try to get that. And the BPF guys have been working on how to get more of that in as well. But even in the kernel, you'll find bogus symbols, and they'll trip you up. And we're guilty of that in ZFS on Linux as well. Though I think I fixed that, but you may do some old traces on old binaries, and it'll be or old kernel modules, and they'll be wrong, which will cost you a day or two of wrangling. So I think we're out of time. So thank you very much for attending.